Hello and welcome to the iRevise supplementary series for GCSE Physics. Our topic today is electromagnetism, and what I'd like to look at specifically across the various GCSE exam boards. You'll see Faraday's law and Lenz's law. You may or may not know those laws by name, but you will see them in the type of material you learn in your syllabus. Okay, it involves electromagnetic induction, the generator effect, motor effect. Yeah, we will not be reviewing anything to do with basic magnetism, north-south poles, attraction, repulsion. We might talk about a few questions about how would you plot the magnetic field around a solenoid, that sort of thing. But just for basic bar magnets, we'll leave that. That's pretty key stage 3 if you ask me. Okay, this is to supplement things which are not in the junior certificate, okay, which is why we're talking about electromagnetic induction. We are not doing any static electricity or current electricity, purely electromagnetism, okay? So that means we'll talk about the national grid to a certain extent, but only in the context of transformers and how we get electricity pumped out to us. So we will not be delving into comparing different power stations, how they generate the electricity, and the pros and cons, and efficiency, and how they work. We won't be talking about any of that. We will not be talking about electricity in the home, main supply, ring circuits, circuit breakers, fuses, stuff like that. We're not going to be doing cost of living and calculating your kilowatt hours or any of these types of things either. We will not be touching anything to do with Ohm's law, calculating resistance, voltage, power of a circuit, series, parallel, all that stuff. I assume that's all covered elsewhere in the iRevise archives, okay? But what we will talk about specifically when it comes to electric circuits will be potential divider circuits, LDRs, thermistors, and how certain devices work and that sort of thing. Relay switches, okay? Things which involve an electromagnetism element. And we need to get on with things, so let's go. All right, let's start off with an OCR question. This is from the 21st Century Science Physics A. This is a typical experiment you might have seen in your classroom. You drop a magnet between a coil hooked up to a data logger, and you get this little graph. Why is there voltage across the coil? When the magnet passes through the coil, some of the magnetic field lines are cut by the wire. The wires cut the magnetic field. You could say there's a change in magnetic flux. You'll see that the flux density is going to change. It's going to get higher and it's going to get lower, and that translates to an induced voltage. Lots of information there. We'll see what the mark scheme says. Part B, the effect used up above there is used in power stations to produce electricity. Yeah, this is the generator effect. Okay, it's electromagnetic induction. Compare the electricity produced by a power station with the electricity produced here. Well, this experiment, we only had a one-time graph kind of going up and down. It needs to be continuous. We can't even have the magnet dropping through one big large coil, because it'll just be one low bit and one high bit. We need this to be happening continually, so we need to have, usually we've got some coil rotating in a magnetic field. Yeah, what other information from the graph? Well, we'd want this to go on for a lot longer. The same effect is used in transformers, right? Okay, so what do we want to say here? Draw one line from the beginning to the correct end. We want transformers can either increase or decrease the size of an alternating voltage. That's what you need for a transformer. Okay, and then here we move along here. We're going to fill in the blanks, describe what's happening here. So 3 marks, so probably you got a mark for each pair of correct answers here. So what do we want to say here? A changing voltage across the primary coil is going to cause a changing magnetic field in the core. No, wait a minute. A changing voltage across the primary coil is going to cause a changing current in the primary coil, so TU, which causes an R, changing magnetic field in the core. Okay, and then this will induce a changing voltage across the coil because of the electromagnetic induction. It produces a voltage. If the circuit is connected to something, then you will get a current. So you're not inducing a current which gets you a voltage. You're actually going to be inducing a voltage across first, P, and then that will cause a Q, a changing current. Right on to the answers here. We've got electromagnetic induction. You could just say induction, because if the magnetic field is changing, is that all they needed? Why is there a voltage across the coil? and they want you to, you can just say electromagnetic induction. Ugh. I think the magnetic field is changing. The magnetic, you could call it the flux density is changing. You can induce or induced as one mark. Idea of a magnet moving near a coil leads to voltage. Yeah, you can just say electromagnetic induction. Interesting. I suppose because they say the effect described in part A, and it's one mark, you could say, yeah, it's electromagnetic induction. I suppose you could get that from looking at part B. Speaking of part B, yeah, obviously the voltage at the power station is much higher. The experiment is only one cycle. The power station is continuous. That's what I was saying. Higher frequency. It said how they compare, but I guess you could have had the similarity of them both alternating current. I'd said it's continuous at the power station, and yeah, it should be obvious that the voltage is much, much higher. And at higher frequency goes faster as well. Okay, that's how we had locked that. Okay, and then yeah, we had TU, R, P, Q, didn't we? We got them in the right order, and so you've got 3. You get 2 pairs, and then R by itself. Okay, and these are some possible common answers. Okay, and next we've got an Edexcel June 2016 paper 2 here. Add 2 arrows of the magnetic field lines to show the direction of the magnetic field. Okay, well, we know that magnetic fields go from north to south, so we could have some of these here, we could have some of these out here. We could draw some using our right hand grip rule. Thumb goes into the plane of the page, which means that these arrows are going to go this direction. So you see on the left they interfere, they go in opposite directions, and that's why there's a area of weakened field here, whereas here they're going to build up, and these field lines are closer together because the field is stronger. Okay, draw an arrow on the diagram to show the force on the direction of the wire. Well, think of this as a compressed spring. When the spring bits are closer together, it's going to be more likely to spring out, whereas if they're far apart, that's the direction it's going to go. So I would say, if I draw my arrows up here, I'd say the wire is going to jump out to the left. Label this arrow F. 2 marks. Do what it says. Okay, so we've got arrows on 2 or more lines, either from north to south or clockwise on the loop. So I did both. You could do either one of them, I suppose. Okay, it's going to be a horizontal arrow going to the left. Okay.
To the left, to the left. To the left, to the left.
Just a real quick question. I believe it's probably covered in all curricula, even the junior certificate, but it bears repeating. It's an important one. What's the role of transformers J and K? Transformer J is going to step up the voltage, make it a high voltage, which will lower the current. The cables are going to send along the electricity at a very low current, and because of the Joule effect, the Joule heating, which is I squared R, we're going to reduce the heat loss, we're going to reduce the power loss. That's why it's at high voltage. And then in order to get to be something which is safe for us to use, we need to step down that high voltage using a step-down transformer at K, so that it is something a little more safe for us to use. Okay, transformer J increases the voltage, decreases the current. Yes, it means less energy is wasted. Okay, less heating, I had said, less energy is wasted. I always forget this part. Why? Because it increases the efficiency. You got a mark for that. And then transformer K is going to do a step down. It's going to decrease the voltage to be safe. Okay? This is the one I repeatedly have a problem remembering, is this increases efficiency. That's why it's been done. The role of the transformers and the reasons for their use. I talked about the roles. I hadn't talked about the reason. Okay? So it will mean less energy wasted, and we do this so it's more efficient. Right, this is from a January 2013 paper 1. I'm not going to go to the previous question because it's about electromagnetic waves and sound waves and stuff, but this part C is a very excellent question, and something which I know Edexcel and maybe a few other exam boards are going to want you to know the details. Describe how a loudspeaker uses electrical energy to produce sound waves. Okay. Well, I mean, we could right away say a few things if you wanted to. You could just say, hey, I know about the sound waves. If you've ever seen the speakers bumping, okay.
I like this song.
Okay. You know that when these things vibrate back and forth, they create longitudinal waves, which are the sound waves. Okay, so we know that's how sound waves are produced. All right, this is a head-on view of the ring magnet that you see here in cross section All right, and so what has happened is that it is connected. Okay, the South Pole's in the middle, the North Pole's on the outside. It's around the whole ring. Okay, anyway, what's going to happen here? You know, we're going to send in an electrical supply. You know that sound wave is going to be changing. It's going to be oscillating. It won't even be sinusoidal. It'll be far more complex than that. So it'll be changing current. And if it's a changing current, or you just want to call it alternating current to be simple, okay, that changing current, that alternating current is going to create a changing or oscillating magnetic field in this coil. Okay, this is a cross section of a solenoid wrapped around that South Pole, and when we run a current through there, we're going to create a magnetic field. When we run an alternating or oscillating, a changing current, we're going to have a changing magnetic field. That changing magnetic field in the coil is going to interact with the magnet. You know, since it's wrapped around this South Pole, it'll be interfering with the magnetic field going across here, you know, going in from the north into the south from all areas. And so it's going to cause this coil to experience a force. That force is going to be determined by how strong the changing magnetic field is, all right? And you will get either some small oscillations, you get some large oscillations, but this is how we get different volumes. This is how we get different amplitudes of this cone moving. The larger the force experienced, the larger the amplitude, the louder that sound is going to be, okay? I've explained it all how it's going to go. We'll look at the mark scheme to see how they break that down. All right, here we are. These are the relevant bits here, okay? And any 5 points, and there's probably about 8 or so of them, okay? Here's what you could say. Current in the coil, 1 mark. It's a changing current or alternating current. You've already got 2 marks out of 5 for talking about it being a changing current. You know that currents produce magnetic fields in the coils. You know it'll be a changing magnetic field. Look at that. That is already 4 out of 5. And if you don't know anything else, that's that. And you could just say, hey, it vibrates. It creates a longitudinal wave. You'd need to say longitudinal wave because it's a sound wave, and it won't be a transverse wave. But that's easy 5 marks right there. Okay, and you don't even really need to understand the mechanics, the physics of how this is working. But let's move on. Okay, this changing magnetic field is going to interact with that permanent magnetic field. And again, boom, done. You don't even have to talk about the sound waves. That's it. Okay, if you wanted to talk about reference to Fleming's left-hand rule, you could. You could say, hey, you know, you want to draw on the diagram. You could talk about the if this is a coil here, this little circle, if you want to say, hey, the current's going clockwise, it's going to interfere with my field lines going across this way, it's going to push this coil either out of the plane of the page or into the plane, it's going to go to the right, go to the left. You could get into that if you wanted to. I don't think you need to get that complicated. Okay? And here, the force on the coil will be experienced because of these interacting magnetic fields. That causes the coil to vibrate, and because that coil is connected to this paper, this cone, okay, then that's why it makes a longitudinal wave. It's pretty straightforward. And like I say, you can already get 4 marks for just saying something. You could get that in one sentence. You could say an alternating current running through the coil produces a changing magnetic field in the around the coil. Boom. And there you go. That's already 4 out of 5. It is an easy question, but one in which you will need to practice. Okay, and here we've got a rechargeable, I'm going to call it a flashlight, because to me a torch is something that you light on fire and wave around a cave like Indiana Jones.
I know in England they use pounds, not dollars.
Oh, thanks, Matthew.
They call an elevator a lift.
Silly people, aren't they?
And they call a flashlight a torch.
Yeah, and what do they call a torch?
Anyways, it's rechargeable light source, let's say, and the inner workings of it you see down here below. There is a magnet that moves in and out of a coil. Now, in this design, it looks like the magnet's moving in and out. I'm wondering if you've got a heavy magnet, if you couldn't just kind of have it attached to this cap here, and you just have this coil swinging back and forth. Some designs might have that as well, because it doesn't really matter if the coil is moving or the magnet is moving. They are moving relative to one another, and that's what's causing the change in the flux density. That's what's causing the change in the flux, okay? If I've got a magnet way over here, all right, some field lines some field lines will not go through that coil, okay? But if I've moved that magnet closer, now you can see all the field lines, okay? Even when they go out and around, they're going to go through that coil. So the closer you are, the stronger the flux going through there, and then when it's changing, this is what induces that voltage, okay? And this is how we are charging the battery. How is the voltage induced? Okay, well, we could say that the magnetic induction induces a voltage. We could be probably a little more detailed. When there's a change in the flux density, when there's a change in the number of field lines being cut by the coil, we will induce a voltage, something along those lines. All right, state one way to increase this voltage. We've already seen this question before. We know that we can have a stronger magnet. That's the... Remember, the EMF induced is going to be equal to BIL. So stronger magnet. Yeah, we could have more turns. Coil with more turns. If you have more turns, you've got more of the length of the wire in that reacting with the magnetic field. And we could shake faster. Shake that thing faster, all right, and it'll charge more. Okay, here's the inside components of the torch. There's the LED that's going to light up. Here's the coil, and I guess the magnet goes back and forth. I would have thought that a heavy magnet going back and forth, smashing against this equipment wouldn't be what you want. I would have thought that you would want a free, loose and lighter little coil moving back and forth. But maybe there's a problem with where these leads connect. I don't know, but that's what I would have thought. Anyway, when the LED is on, what does it show? Well, it doesn't show the currents alternating because we know that LEDs only let current go in one direction. Okay, this doesn't look to be like a warning light, so I don't think it means there's a fault. Okay, and it's not a standby light. I mean, these multiple choice really are a bit ridiculous. It means there's a current in the circuit. Yeah. Okay. Manufacturer states that an LED is more efficient than a filament lamp. Explain this in terms of energy transfer. Okay. Well, we could say that we know that a filament lamp, what a filament lamp does is it actually gives off far more heat than it does light. Okay. And really, if you remember, if you've ever seen the old-fashioned light bulbs, they were quite hot. LEDs, they don't give off heat. Let's take a look at what they say. Right. So how does this thing charge? As I'd said, the field lines are going to cut the coil. Okay. The magnetic flux is changing when it gets in and out of the coil there. You must refer to the relative motion. I said it was relative motion. You could say the coil moves around the magnet or the magnet moves in the coil. Either way. Okay. You can't just say it's a moving magnet. You need to say it's relative to the coil because it changes how many field lines get cut. All right. Wire cuts the magnetic field, 2 marks. I had a colleague years ago when I got into this teaching physics racket who would tell students on the IGCSE to just memorize statements like wire cuts the magnetic field or the field lines cut the coil. I'm not a big fan of people memorizing things. Okay, I don't think it helps your understanding and it gets you into trouble. But these are statements which are basically the only real way you can kind of explain what's going on in a nice way anyway. So it's not about memorizing these words. It's about being familiar with vocabulary terms and describing the scientific language. That's the way I would look at it. Okay, how to increase the voltage? A faster, more energetic shaking. Yeah, you could say more turns on the coil, but that's changing the nature of the flashlight. Okay, a stronger magnet. Again, it's possible that that's true, but when you're out in the wilderness and you need a flashlight, you're not going to have more copper wire or different types of magnets to replace. So the only thing you can really do when you actually need to use it would be more energetic shaking. Okay. Yeah, we said C. That was very obvious. LEDs waste less energy and they produce less heat. Okay. Oh, yeah. So they were talking in this question in terms of energy transfer. Now, this is a bit misleading, okay? Energy transfer, but then they get talking about efficiency. That's the efficiency equation that we just saw, don't they? Okay? We can say LEDs waste less energy or produce less heat, or the other way around. So you could say the filament lamps give off more heat. They produce more waste energy because we give off more heat than we do light. Okay, but in the olden days, let's face it, light bulbs were used not only for light but also for heat. Think about chick incubators and that sort of thing. Anyway, this second point is for you to talk about useful energy output divided by total energy input. The efficiency, that's the equation for efficiency. The efficiency is larger for LEDs compared to the efficiency for a filament lamp. Yeah, I mean, that's what you're saying. You're saying, hey, because the LED wastes less heat energy, it's more efficient. Now, in terms of energy transfer, it's a bit misleading. So you see in this question, they want you to talk about efficiency. Look for these little nuances, and this is why we do past papers, so we can see kind of what they're actually looking for when you read a question. Okay, a student passes a thick wire through the cardboard here and draw on the diagram the shape and direction of the magnetic field produced. Well, I would imagine it should look like this if you use your right hand thumb rule. Thumb pointing up in the direction, fingers curl in the direction of the field, something like that. I'm not sure how they want you to draw this. I would suggest we get the arrows the right way and we would show concentric circles, but with a larger distance between the second and third than between the first and second. Why? Well, because the further away you get from the wire, the weaker the field. It's 3 points, so I would emphasize that point. Maybe they want us to draw 3 lines even. I don't know. Okay. Describe a method the student could use to show a magnetic field is produced. Very typical question. Why don't we place some iron filings all along there, then you give the card a little tap, and they should line up in the magnetic field.
All you gotta do is tap it in. Don't worry about it. You're still in good shape. All you gotta do is just tap it in. Just tap it in now. Hey, just tap it in.
That's a pretty common question and answer. In a relay, an electromagnet is used to operate a switch. We kind of talked about this in a previous question. All right, so the relay is used to turn off another circuit. Okay, so this will be a small voltage which will cause an electromagnet, which will pull this soft iron armature towards it. That pivot will make these contacts, and then you're going to have a different circuit be activated. Okay, the table gives some statements on how the relay works. Put the numbers in the box to show the correct order. 1 has been done for you. Not 1, 6. Ha ha ha. Anyway, what do we do first? The switch is closed. The switch is closed, I would say, is number 1. The electromagnet is magnetized. 2, it's going to attract the soft iron armature. So the armature is attracted and rotates, and the contacts come together and the lamp goes on. Yeah, so that's kind of what we had already just talked about when I analyzed the diagram. Explain why the lamp turns off when the switch is opened. Well, it's the same type thing when this, the switch is. So I would say the electromagnet demagnetizes, and usually in some of these there'll be a spring and that sort of thing. But when it demagnetizes, because of this pivot, because of the way these contacts are, they probably forced the thing back open. Let's see what they say on this particular setup. Okay, so we had 3, 5, 2, 4, didn't we? Yeah, that's fine. And what are they saying here? All 5? Yeah, okay, we got the 3 marks there. What are they saying here? Okay, the idea that the electromagnet loses its magnetism, check, that's 1. And one of these 2 things. It opens the contact, which breaks the lamp circuit. Good. Or the armature is no longer attracted and the armature moves away. That's, I think, what I was kind of hinting at. So either one of these, but notice they want you to break the lamp circuit. Careful what you're talking about. Up to the earlier part of the question, let's see, at least 2 concentric circles. They always want that. Anti-clockwise direction, single circle centered in the wire and parallel to the plane of the... Well, that's how we had drawn that. Okay, so 3 marks. They weren't really... ignore spacing. They didn't really care about the spacing in this case. It should be... hey, some exam boards, some questions, they will want a larger distance as you get further out. So just be aware. They want a single circle centered on the wire and parallel in the plane of the card. And if you just draw 1 circle, you got a mark. The rest is extra here. Okay. Yeah, here, iron filings used. Tap the card. Boom. Done.
Just tap it in. Just tap it in. Give it a little tappy. Tap, tap, tap-a-roo.
Okay, or you could have done plotting compasses on top, maybe give them a little shake, and multiple compasses should line up the arrows in the different directions to show the field. Yep, that's fine. You could use a magnet or another current carrying conductor, bring them towards each other. You know that depending on the direction of the wire, if you bring another wire with a current flowing through it, those wires will either repel or attract. That's where we get our definition. Well, at least where we used to get our definition of the ampere from. They changed that in 2019. And this is a June 2014 paper 1 from Edexcel. Explain why the coil starts to spin when the switch is closed. Again, very kind of straightforward, I would hope. We've got a current running, so we've got a current running through a coil. Okay, the current running through the coil causes a magnetic field around those wires. Those magnetic fields interact with the permanent magnetic field lines. They will experience a force, and because one side is experiencing a force upwards and the other side is experiencing a force downwards, there will be a torque along the middle here, and it will rotate. I'd say something to that effect. This is just how to make it spin in the opposite direction. Reverse the connection. Reverse connection of these alligator clips. Switch the battery around the connection of the battery. You could flip the magnet. You could exchange the magnet poles as well. Okay. How could you make it spin more slowly? Besides adding in a resistor, what you could do is to make it more slowly, you could reduce the number of coils. You could move the magnets further out, making the magnetic field density a little lower. Just use weaker magnets. So, how do we get this thing to spin? There's a current in the coil, we said. Okay, in the coil. The magnetic field around the wires in the coil, they interact with that of the permanent magnets. There is a force. Yep. And it's, reference to the left-hand rule. So you could talk about the left-hand rule. Force on one side, down on the other makes it rotate. Good, that's what I'd said. Lovely. Okay. Make sure you got all your 4 points in there. I think a lot of times students, they get the idea, but they just kind of rush through, and they aren't really, this is a nice one to remember. There is force as a result of interacting with the magnets. The more detailed you can be, you can see you can probably get 3 points out of just one sentence. So watch and make sure you've got the detail. Right, we talked about reversing the polarity, reverse the current direction, swap the magnets over, right, we had said, okay? And then here, to make it go slower, reduce the current. Yeah, I guess if you reduce the current, you throw in a resistor. You can do that. Reduce the current, reduce the voltage. We were down to one battery in the diagram. Oops. Don't say battery. That's a cell. Okay? A battery is several of those together. I know in our layman's terms in English we call that a battery, but that's actually a cell. So if you could somehow reduce the voltage, use I guess a cell that's nearly dead, nearly flat. Okay? Increase resistance. Okay, yep, pop that in. Weaker magnetic field. So however you want to describe that, move it away, use weaker magnets, that sort of thing. Good, well done. Okay. Gotta love Transformers.
Transformers, more than meets the eye. The Transformers, robots in disguise. The Transformers, more than meets the eye. The Transformers.
Here, state the equation linking the power output and input. Yeah, well, I mean, I think we had said in a previous question, primary and secondary, IV, it should be the constant for all the way through. Calculate the current output. Okay, so the current output is the secondary. It'll be current primary. It'll be, and this is the same side of the equation, so don't change anything. I know students get mixed up and move things all around. So what do I have here? I've got 2 amps, 230 over 110. Right, so that looks to be about 4.2 amps. We'll see. I've noticed that they've given us the number, linking and turns. There we go. All right. So now this one is a ratio, I believe. Okay. We know that the more turns, the higher the voltage. So they need to be on equal sides of the equation. There's a proportionality. Okay, and now they want us to calculate the number of turns. Yeah, because that's the one we didn't have. All right, so the number of turns is here. I'm going to swing my NS up. I'll keep my NP here because I've not moved anything, and then this fraction is going to go to the opposite side, and it will be a reciprocal. Okay, the 110 over 230, and that'll be multiplied by the number of turns, which I believe was 12, which was 1200. Okay, and the secondary, because this was a step down transformer, I should be used to having a ratio here which is less than 1, and that gets me about 574 turns. How does the transformer work? 5 marks. Whew. Okay. You should include 2 coils, an iron core, an alternating supply. Well, yeah, man, I could not have made this any easier for how a transformer works. Okay, now if we want to do a little diagram, what I'll do is I'll go up using their diagram. Okay, what we have is an alternating supply. Let's just wait for that. Okay, but what happens is you basically have an electromagnet here. You've got the coils around the iron core. Okay, you have an electromagnet there. Okay, now because it's alternating, it means that the instead of being north and south always, it's going to be alternating. All right, and that's at 50 hertz in the UK. All right, or 60 in the US. All right, you're going to have alternating magnetic fields. And because the magnetic field in the iron core is changing, we have a changing magnetic flux. You know that a changing flux will induce a voltage across a wire if there is a coil. Okay. All right, if we were to go back to this previous question just for a moment here, we note that we can cause an induced voltage in this coil of wire two ways. Either we move the magnet into the coil, or we could keep the magnet stationary. We could move the coil around the magnet, okay? Either way, what's happening is the magnetic flux lines, okay, the field lines are going to be cut by that coil, and the flux density entering that coil is going to change, all right? And we can do it one of 2 ways. We can either move the magnet or we can move the coil, all right? It's all relative. Now, if we go back to this question, okay, we're doing neither of these, but yet we're still having the magnetic flux changing. How is it changing? Because it's an alternating supply. So that's the beauty of that. And because it's an alternating supply, we will induce a current, okay, in the wire, or a voltage across that wire, all right? And that's how we are getting a new voltage being produced, okay? And then is it a step up or is it a step down? We know that the number of coils, the number of turns in the coil will dictate the strength of that new induced voltage, okay? That's basically what's going on. That's how it's going to go. We've mentioned the 2 coils, the alternating supply and the iron core, so there we go. Let's see what they say in the mark scheme here. So let's see. Oh, input power equals output power, right? Or give that equation, okay? You can do in and out or 1s and 2s, however you want to do. We like to pretend that transformers are completely perfect.
I am autonomic perfection.
That is to say, no energy loss is what we like to assume. And yes, our calculation was 4 amps. I had 4.2. I guess there's some rounding. Okay, 4.2. Talk to your exam board about how they do the rounding, if there's a sig fig issue and all that stuff, okay? And then here, the last bit, so we have the correction. Yeah, so make sure you know if you got primary on top for both, secondary on top for both, however you want to write it. But it is always a ratio because we know the voltage is proportional to the number of turns. And then you rearrange and you get your number, and we should have had about 570. Okay, I think I had 574. Good. Okay, and the last bit, how does the transformer actually work? Well, it will either step up or step down the voltage. Okay, we kind of didn't really get talking about that. That's not explaining how it works. That's explaining what it does, and you can get a mark for that, so that's nice. Okay, we know that we will produce a magnetic field. We know that it's changing. Oh, I said, hey, 50 hertz. There we go. We know that the changing magnetic field in the core is going to induce a voltage in the secondary coil. Okay, you could also mention that the core strengthens the magnetic field. That's true. You could have a very primitive transformer of just two coils side by side, and it will work, but it's not going to work as well. So mention the core of why it's there. Field lines interact with the secondary coil. Yeah, the changing magnetic field lines, that changing flux is going to change in the secondary coil, which is what induces the current we had said, right? Okay, and it won't work with DC. You could say that. So plenty of things you can say. I think if you break down the function of a transformer to say something like they say here in the question, and you can decide for 4 marks or 5 marks or 6 marks, but talk about what's going on in each of the coils, talk about what's happening because of the core that you need it and that sort of thing, and talk about what's going on because of the alternating supply. Simply that you need it is fine for 1 mark, but you can get more for what you need. So these types of questions can be anywhere between 3 or 6 marks depending on your exam board. Make sure you can answer them. All right, another AQA. This is June 2017, paper 3. This question looks to be like it's an experiment. Student investigates how changing the size of the current in the coil wire affects the distance moved by the paper cone. 2 variables that they should control. Strength of the magnet, maybe the distance moved. Are we going to move the size of the current in the coil? So you're going to want to move the magnet at different speeds, maybe. So either the same strength magnet at different speeds or different strength magnets at the same speed. Let's see what they're looking for. Okay, so strength of the magnet, allowed distance between magnet and coil. Nothing about the speed. I guess the speed is what they're doing for their different current values. Number of turns in the coil, yeah, that should be constant. And stiffness of the elastic bands. Okay, fine. They don't really explain much about this setup, and so it's a bit... anyway, moving on. Here are the results. Okay, so when the current increases, how much does the distance moved increase? From 0.5 to 0.9. So 0.5 is about 1.5, and 0.9 is 2.75. I can't draw on here, so we'll just kind of go, so 1.3. That's kind of what I was thinking. State 2 conclusions that can be made from the graph. Once you get to a certain current, that's the maximum that cone's going to move. It tends to increase at an increasing rate, and then it's constant for a bit, and then it increases at a decreasing rate. Is that what they're looking for? As the current increases, the distance increases. Yes. Above 1 amp, the distance does not change. Right, it's leveled off. Okay, doesn't matter. And between 0.3 and 0.7, the relationship is linear. Yeah, that's kind of what I'd said. Yeah, I noticed. To me, it was 0.4 to 0.6, but they say between 0.3 and 0.7. So anything else you might want to reference there, pause and take a look at what else there's left. This is a June 2016 paper 3. Again, we'll do a few transformer questions. There's an alternating current. State what is produced in the iron core. It's an alternating magnetic field. Okay? That's what's happening in the iron core. An alternating magnetic field is being produced. Here they want us to do a calculation. I can't show us what that is. We've seen this already. So we'll just briefly look at the mark scheme. Yes, magnetic field that is alternating. Here's your 230 over 11.5, so it's 20. Okay, that's how you would have calculated that. Let's move on. In most transformers, the power output is less than the power input, and it's because transformers are not efficient.
Here is your cut.
This is all.
Oh, I'm afraid so, Shrapnel. The transfer process is costly and uses a great deal of energy. Maybe we'll do better next time.
Okay. Here, this is a lovely looking question. We've got investigating how magnets can be used to produce potential difference. So the magnet is here. The magnet is students quickly lowered the coil. So okay, so here's a situation where we don't move the magnet, we move the coil around the magnet. Okay, and they recorded the potential differences in this table here. 2 different students. Results kind of similar. You can see they start to get a lot higher as we move on for student 1. Give the resolution of the voltmeter. I would say hundredths. It goes up to the hundredth of a volt because that's what our measurements were in. Okay. Reason? Well, because that's what it said. That's what we see. The two students used the exact same equipment. Both students recorded differently. Give the reason why student 2 got different results from student 1. Well, I don't know. Maybe did they move the coil the same speed? It hasn't said what they've done. They've used the same equipment, but procedure, maybe their procedure is slightly different. I bet you they're at different speeds. The students decided even though the results were different, there's no need to repeat the investigation. How do the results show the investigation is reproducible? I mean, they're kind of close. This last level, I'm not sure what they're looking for here because it's only 1 mark, but we'll see. Name the process which causes the potential difference to be electromagnetic induction. Transformer has been developed that can be used with many devices. Suggest one advantage of having a transformer that can be used with different devices. Well, different voltage inputs. You see this with laptop chargers and your game power packs and cell phone chargers. You can be anywhere in the world and you can use whatever voltage they have. Let's see. Yeah, transformers are not efficient. The resolution, 1/100th of a volt because there is a change in potential difference each time the number turn because all the results are to 2 decimal places is what I would have said. If there was results to 1 decimal place, there might not be a difference. I suppose if you were to get, because this would round up to 0.2, that'd be 0.2. This would round up to 0.3, that'd be 0.3. But what are they saying here? Because there is a change in potential difference each time the number of turns changes. So when we change the number of turns here, we change the voltage, but I don't know one reason why the resolution is... Oh, why it's suitable. Okay, why is it suitable? Not why is that the resolution. Yeah, it's suitable because they're not going to be rounded in any way, and we can actually see differences. Okay, so I agree with that. I think student 2 moved the coil a little more, probably at a different speed. Okay, do not accept the student 2 moved the coil faster. This is student 2, and it must be slower because the voltages are not as high. Yeah, okay. Both sets show the same pattern. Yeah, I mean, this is... if it's repeatable, they got the same pattern, I guess. Results are similar. Don't say they're similar. It's the same pattern. It's not about the numbers being similar. It's about showing the same path when you were to graph those numbers. Okay, EM induction, and then the transformer. It's more economical, cheaper for the consumer, cheaper, easier to replace. Yeah, because you can use them anywhere. Since fewer transformers need to be made, less resources are used. Okay, fewer transformers needed, fewer sockets are needed, environmentally friendly. What was having a transformer that can be used with many different devices? Well, we don't want we don't want to make more transformers than is needed. Okay, AQA paper 3 June 2015. Here we've got a wire here. Explain why the force acts on the wire when the switch is closed. Well, here's your left-hand rule. You're going to have a current running through. Let's see. It looks to me like we would have current going from X to Y, and so current going left to right, field going into the plane. The wire's going to jump upwards because it's going to experience a force acting on it, okay? Something to that effect. Draw an arrow in the direction of the wire is going to move. Yeah, okay. What's the effect? This is the motor effect. And student replaced the battery with okay, it's not going to work with is it going to work with an alternating current? Might not work if it's going. It might be moving too fast for the wire to respond. We'll have to see. Describe the movement of the wire. Well, maybe it moves up and down then. I guess it would be oscillating. I guess. Give the reason. Well, because the current is changing direction, the force, according to our left-hand rule, is going to be in an opposite direction. Is that what they want? Close the switch, makes current go through the wire. It's got a magnetic field around the wire, and that will interact with the permanent magnetic field. Yeah, something to that effect. Good. It's going to go upwards. It's the motor effect. The wire will move up and down. The wire will vibrate. Oh, okay. I've not seen that in a demonstration, but okay. And it's continually changing direction. That's why. Good. Okay, and I've got a June 2019 from Edexcel here. We've got a student investigating a transformer. Okay, and there's my graph. Not bad if I do say so myself. That's a pretty darn good-looking curve of best fit considering I'm on a tablet. What's the relationship between output voltages and number of turns? Well, I would say it's inversely proportional. We'll see what they say. State the formula linking input and output voltages as the turns of the radio for the transformer. Well, I believe our voltages, input and output, is related to a ratio of the number of turns in the input and output, but we'll see. Okay, and then the input voltage is 6.8. Calculate the number of turns in the secondary coil. All right, so I'm going to rearrange. You know, maybe what I do is I just flip the whole thing, if that makes it easier for you. So I'll get my primary turns, and then okay. Now it says at the beginning that the number of turns is 10. But that's just incrementing each of these by 10. I think you just choose any old value off of the graph and plug it in, and you should be fine in calculating. Remember, this graph was output voltage and primary turns. Output voltage and primary turns. They give you this 6.8 here. So just plug in some values from the graph, and you should get your answer. Okay, mark scheme. Points should lie on a very good curved line. That's what I've got. I've plotted them all correctly. I'll get a mark, 1 for the curve. What's the relationship? It says allow unqualified inversely proportional for 2 marks. They say here you could say as a number of turns increases, the voltage decreases, but at a decreasing rate. That's fine. That's what inversely proportional means. Here's your formula. Substitute in some values for here. You get them from any row of the data from the table, right? Good. And you should get an answer. It says somewhere between 56 and 60 for the number of turns. They get 58. So yeah, whatever you plug in there. Okay, we've got an electric toothbrush charger here. This is from June 2015, paper 2, and well, this is how these chargers work. They use electromagnetic induction. Okay, and so you've got the coil in the charger, you got the coil in the toothbrush. You've got an input voltage and you've got an output voltage. Name the type of transformer that reduces the voltage. It's a step down. Explain why the core is made of soft magnetic material. Iron is soft, so it will not be permanently magnetized, and it will allow, therefore, for an alternating current to produce an alternating magnetic field inside, which is what we want in order for induction to work. The equation, yeah, here we go again. So it's primary over secondary, number of turns. I've been alternating between capital and lowercase n. It doesn't matter. You decide what you want to do. Here we do is some calculate what's the output voltage. Okay, so secondary. I'm going to swing my up to the top, and I would have had an ns over np. I just, reciprocal both of these, and I guess we'll plug in our numbers here. We'll see what our answer is just in the interest of time. Step down transformer, good, right? So soft material loses magnetism easily and so quickly it will not be permanently magnetized. Okay, and then it allows an alternating field, which we also need. There's our formula. There's our equation. We plug in the numbers. Okay, 2.5. Happy. Okay, got a January 2016 paper 2, again, Edexcel. I remember giving this to my students a year or two ago, and this is an interesting type question. So in the diagram, sketch the magnetic field caused by current in the coil. It looks to me like we've got current going over the front. So if I curl my fingers in the direction of those arrows, my thumb's going to point up. We're going to have a north pole up here. You want to try to draw it symmetrically. You could have lines coming, yeah, something like that. Let's see what they're looking for 3 marks, but I think we probably have that. Yeah, this part is lovely. This is a really good question. So coil suspended vertically, they're free to swing, and a second identical coil is placed beside it. Current is going to pass through the coils moved together. So you see they're identical. So what's going to happen, the coils move together. When the current in the right-hand coil is reversed, they move apart. Explain why the coils move in this way. Well, if it's in the same direction, then they will both have little mini magnets little mini magnetic fields lining up the same way. And so on the one end, whether it's a north or south, doesn't matter, it will be the opposite for the identical ring because the current's going the same direction through them. And so there will be an attractive force between the two induced magnetic fields. Whereas the other way, depending on how you drew it, like let's just say for argument's sake there's a north pole here and a south pole here. That means when the current's going the opposite direction in the other coil, it will be north on the outside and south on the inside. And it could be north on the inside and south on the outside. It doesn't matter. The point is you will have similar or like poles repelling. So something along those lines. Let's see what they say. So you want at least one straight vertical line through central, and this is typically how you draw your diagrams. Okay, you'll have one going through. You want some symmetry. Any field line circling the wire. Okay, at least one peripheral loop, and field directions correct and consistent throughout. Okay, now circling the wire or at least one peripheral loop. So I had peripheral loop. So in this diagram, I had one coming out here and kind of branching. If I wanted to do other loop ones, I could, but I think those three was enough we saw. Okay, and the directions need to be correct. Okay, and then what happens with the loop, the identical loops? Yeah, magnetic fields are interacting. Okay, they will be an attraction or repulsion, and by reversing the current in the one loop, you will reverse the magnetic field, and some comparison with magnets about like repelling and unlike attracting, opposites attract, that kind of stuff. Right, okay, so I mean, that's kind of what I said. You definitely, for yourself, I'm just trying to go through the physics of things. You need to be practicing these questions for yourself and getting your details and your articulation down pat. Okay, and another lovely question here. This is from 2014, paper 2 at Edexcel. We've got two metal rods. They're just going to sit in this coil of wire. When a direct current is supplied to the coil, a magnetic field forms, and the metal rods move apart. Explain why the metal rods move apart. Okay, well, we're going to put a coil around here. Let's just say that the current's going this way. And if that's the case, we're going to have a north pole a north magnetic pole coming out in this solenoid. Okay, now because these are metal rods, which we are assuming are magnetic, okay, they are made of some sort of magnetic material, it means there's going to induce a magnetic field in each of them. And if they both have their north poles side by side, then these like poles will move apart, and you'll see these rods kind of, depending on the strength of the magnet, they'll move away from each other and roll up to the opposite sides of the solenoid. When the switch is turned off, the metal rods return. Suggest what material? Yeah, well, it's soft. It's soft iron. It's soft magnetic material. The magnetic field is not induced permanently, and so when the current is gone and the magnetic field in the solenoid is gone, the magnetic field in the rods are gone. Something to that effect. There's a part C. The direct current in the coil is replaced with an alternating current. What will happen to the magnetic field? Well, that's interesting. The magnetic field will also alternate, but that will still mean that these rods will change their magnetic polarities at the same time. So they'll still move away from each other. What do we got? Rods are magnetized and repel. I went into a little more detail than that, but that's basically it. Soft iron. Because it's capable of being magnetized, but does not retain the magnetism. And finally, the field in the coil will switch polarity. Field in the rods will be weaker. Oh, interesting. Okay, if we put it alternating current. Okay. Does it make sense that the field would be weaker? Because the field's constantly changing. That strength of that field will follow a sinusoidal line. And if you take the root mean square average, it will be overall. If you're averaging over time, you take the root mean square average, and it will be lower than whatever the maximum was from the direct current. Okay, so yeah, that's an important point to remember. It will be weaker. I said it was going to alternate, okay, with the current, or at 50 hertz, you could say, and rods may not have time to become fully magnetized. Yeah, well, that's the other thing. That's another reason why you might say the field in the rods are weaker, is because it's switching back and forth. By the time these dipoles line up with the field's changed, and so the dipoles move around. And, 50 times a second, that's a lot, okay? So you can talk about, reluctance. You can get kind of hardcore with this, but you could just kind of keep it simple, too. Make sure you understand that. That's a nice question. Okay, and I've got some WJEC questions here. This is paper 3, June 2017. Got a picture here of an AC generator. Complete the labeling of the diagram. Okay, well, we've got a magnet. We've got a coil, or you might call it an armature. And I think that's about that. State why the voltage is produced when the coil spins. Electromagnetic induction. I think we can probably do better than that. I think we can say the field lines are cut by the moving coil, which induces a voltage in the coil. Okay, here we go. AC generator output. The original output is shown on each of the graphs. Draw the new curve. Draw the new voltage curve for the change stated. Okay, magnetic field is twice as strong. If the magnetic field is twice as strong, we will get a higher voltage. Remember that your EMF is equal to BLV, and if it's twice as strong, twice as much. Now, if it's spun twice as fast, this should be interesting. Here and here, so we will have higher amplitude and a shorter wavelength, because it'll be a faster frequency. Okay, what else? Identify the step-down transformer. So we've got 5 different transformers. Output voltage. This is the input. This is the output. Oh, okay. So D is a step down, because that's lower from the 10. It's 4 from the 20, and so on. It's a factor of 5. Identify the transformer that steps up the current. Well, E keeps it the same. Steps up the current. If you step up the current, that should be from lowering the voltage. Identify the transformer with the same number of turns as input and output. That's E. Your input voltage is 2. Supplied to transformer B. Calculate its output. Okay, well, this looks to be times 3, so I'll say 6. Okay, and use an equation, number of turns on the output coil. So I'm going to do NS over NP this time, and that'll be VS over VP. Calculate the number of turns on output coil C given the input has 500 turns. Okay, so that's going to be 500 times I don't know, let's say 300 over 20. So it looks to me like I've got 15 times 5, so is that 7,500 turns? Let's have a look. 7,500 turns, good, happy about that. Let's see, coil and magnet, we were right. Wires or coils cut the field lines, boom, 1 mark for that. Or magnetic flux through the coil changes, you could also say that too. Good, okay. Don't talk about splitting field lines or talk about electromagnetic induction, okay. The coil is cutting the field lines, the magnetic flux is changing. Either of those is fine. Amplitude is doubled, and 1.5 cycles shown. I had done that. I showed 1.5 cycles. Okay. In this case, at least 1 peak and 1 trough, all drawn, but have an amplitude doubled, and 3 cycles shown for the whole graph. That's the second mark. And again, 1, 2, 3. That's what we did. Okay, so you had 1.5 to go, and it went twice as fast, so 1.5 times 2, you should have 3 cycles going in the same amount of time. Okay, D, D, E, very good, all right. I was a little curious about this steps up the current, but that's the step down transformer. Okay, and we had said 6, and we said 7,500. Lovely. Okay, and I've got one more transformer question here. I think that's enough, okay?
Enough! I've seen enough!
State how the construction of a step-up transformer is different from step-down. You can just say step-up has more turns on the secondary coil, step-down has more turns on the primary, that kind of stuff. Put a tick for what we got in. What is this? Diagram shows, investigation. Which would cause the voltage to increase. Increasing number of turns on the primary? No, not on output. Decreasing number of turns on primary? Yes. Decreasing input voltage? No. Increasing the number of turns on secondary, decrease, no. Well, and don't write the same answer for both. Really make sure you're not contradicting yourself. I see students do a lot of that. Explain why there must be alternating current. We need an alternating current in order for the magnetic field to be alternating so that we can induce a current in the coil. Something along those lines, okay? Induce an EMF in the secondary. Okay, what do we got here? I'm going to guess that this goes 100. Yeah, because it's going to be half. That's, yeah, okay. And the relationship you can see is, right, this over this is 2, so this over this must be 2, and there we have it, okay? Plot a graph. Yeah, so we know how it's going to go. Okay, so I've plotted the graph of output voltage versus secondary turns. That's a directly proportional, and before it was a number of primary turns, it was inversely proportional. So this should be no surprises what we see. Describe the, okay, so I would say it is directly proportional. That's the best way to describe it. I know people say it's a straight line through the origin. It's directly proportional. That's what that means, straight line through the origin. Use the graph to find the number of secondary turns required to give 5 volts. Okay, so draw a line of best fit. Not bad. Halfway to here should be halfway down here. So I would say 125. Explain how the graph would be different in the investigation if it was repeated with a primary coil using 400 turns. Well, it was 200 turns. It's going to be 400 turns. If you've got 400 turns, we know that the more turns, the greater the voltage. So it'll still go through the origin, but I would imagine it needs to be a higher slope. It would be a higher gradient, something like that. I would just say it would be a higher gradient still through the origin. That's what I would say. Okay, I don't like it. I don't like how they say it. It has more secondary or output turns than coils or than the primary or a converse. I said a step-down transformer has more primary than secondary, and a step-up has more secondary than primary. I think that's more detailed. I don't like what they've said here, but if you look at how to state how the construction of a step-up transformer is different from a step-down, they're expecting you to, for 1 mark, to just say, well, what's the step-up transformer have that the step-down doesn't? And we would say it has more coils on the secondary. Has more coils on the secondary. That's what they're saying. Maybe I overdid it for 1 mark. That's fine. But the goal is to make sure we understand stuff. All right, how's our pattern here? Ticks on the second and fourth, 1 mark each. 3 boxes ticked, only 1. So 2 and 4. We did that. That's good. Explain why does it need to be alternating. AC creates a changing magnetic field, which we like, which induces a current in the secondary or output coil, and you need to have the first mark linked to get the second. Okay, we had said 100 to fill in that gap. Straight line through the points. We plotted it fine. That's fine. Output voltage increases as the number. Okay, and it's output voltage increases as the number of secondary turns increases proportionally, or you can just say it's proportional to the number of secondary turns. I would say it's directly proportional. It's going at a constant rate. I would say directly proportional. It's fine. 125, good. No tolerance, that's it. Boom. A less steep line, smaller gradient, because each output or voltage would be less halved. Ooh, did I get that one wrong? How would the graph be if the primary coil had 400 turns? Yeah, if this was 400, if all of these were 400, 400 divided by, let's see, so 400, so that's a difference of 8, not 4. So the output voltage would be lower. I've gone from 400 to 100, that's a ratio of 4. So this becomes a 2. 400 to 150. That'd be, yeah. 400 divided by 200 is 2. So this would be 4. 400 over 300. Eight divided by 400, 300. That's 3/4 of 8. So this is a 6, and yeah, this is a 3. So the output voltage is lower. The output voltage would be lower. Does that make sense to me now? Does that make sense to you now? How would the graph be? with a primary coil containing more, it would be more of a step down, wouldn't it? Each output or voltage would be less. It'd be actually halved. Okay. I hope that makes sense now. I know I've learned something. Okay, I've got a question here from January 2016, paper 1. We've got a magnet and a solenoid, and it's going to cause the ammeter to go. We could go through with Lenz's law and our right-hand grip rule and see that when we are moving a south pole in, there will be a south pole here to resist, meaning a north pole there. Your thumb's pointing down, and the current is all facing this way, which is it goes to the left, which is why it goes to the left. Okay, and we could work out the Lenz's law, and we could work out with our grip rule how to make things go to the right. You know, I suppose if you move the magnet up, then this would be a north pole because it would want to keep that south pole there. That would mean that everything would be going this way, and when your current is going this way, it's going to hit the right side. So you could analyze all that if you'd like. Or you could just say, hey, two ways that make the pointer move to the right means it's going to go in the opposite direction. So anything that you're doing here is going to be opposite, but only make one of the things opposite. Okay? So we got the poles of the magnet. We've got the direction. You can't change both of them. Work out for yourself, use your right-hand grip rule, Lenz's law. If you were to change both of them, if you were to move the north pole out, we don't want to do both of them. We only want to change one thing. So if we've been causing the south pole to enter, we are going to pull the south pole out. It's going to exit. Okay? Or you could enter a north pole. Yeah? The north pole could be coming in. Okay, you could switch this whole magnet arrangement and have it going underneath as well. I'll let you work out those dynamics, but I think you know we've got our answers here. The other thing is you could flip how the wires are connected to the ammeter too. Okay, very simple diagram here. This is a little bike generator. Okay, you see that Z here is the coil. And you see that Y here is going to need to be the magnet. And this little magnet's going to rotate, and when it does, it's going to induce a changing magnetic field in the soft iron core, which is going to induce a voltage across this coil, which will cause the bulb to light up. So that's that. Okay, here's a graph of what we've got going on there. Here's a readout of what the voltage would be in time. What's the maximum output? It looks to me like the maximum is 3 squares up, and there's only 5 there. It's going to be a 1.6 volts. Calculate the frequency. Frequency is 1 over the period. And the period is 0.04. We know that 1 over 4 is 0.25, but this is 4 hundredths, so it's going to be 100 times larger. So 25 hertz. What's going on here? The output voltage. Yeah. Well, if you remember from Faraday's law, you probably haven't seen the equation. Okay. Maybe I've alluded to Faraday's law before, but if you change the length of the coil that is moving in the magnetic field, the strength of the magnetic field, or the speed of the wire that is moving in the magnetic field, you will each of these is a factor. Okay. We know that if you move if the wheel turns faster, the frequency will be higher. You'll have more wavelengths completing, more cycles in that same amount of time. We also know the output voltage will be larger as well. I'd say our answer is C. Okay. Apart from changing the speed of the friction wheel, just how the output of the dynamo could be increased. More turns on the coil, or a stronger magnet, not a larger magnet, but a stronger magnet. Make sure you got that. Okay, and the last question here is an efficiency question, so we'll just skip past that like we said we would. Okay, so how could we reverse the needle to make it go to the right? We could reverse the magnet, so we could be putting a north pole into the coil. We could be moving the south pole out of the coil. We could reverse connections on the ammeter. Okay, there's some other things you can do. Take care to read that. You can pause it when you need. All right, let's move on. We had magnet and coil, 1.6. We had 25 hertz, 2 marks, good. C, our answer was higher. Stronger magnet or more turns in the coil is what we had said. Not bigger magnet, stronger magnet. Good. Okay, I've got another OCR, Gateway Science, Physics B. This is Module 6, Section C. We're investigating some electricity and magnetism. On the diagram, sketch the shape. I would say you know you're going to have a line down the middle. We don't really know which direction the current is going. I don't think it matters, because if you say the current is going up on the left and down on the right, your right-hand rule is going to have a north pole on the right side. If you have your current going in the opposite direction, your north pole will be on the left side. So it doesn't really matter as long as you've got a line down the middle, and then maybe have some lines coming out. Okay, and maybe have them loop around. Whatever you do, have it symmetrical so the field lines look the same strength. We'll look at the answer in a moment. And then here, Mia has an electric motor. She can increase the speed by increasing the current. Write down one other way she can increase the motor speed. Okay, again, I can't draw on this particular paper, but if you remember your formula, F equals Bill, the force, the motor effect. B is the strength of the magnetic flux density, so you could increase the strength of the magnets, move them closer together. You could increase the current, that's the I, they've said that already. And then L, you can increase the length of wire in the magnetic field. Now that means you can have bigger magnets, but it also means if you just have a bunch of turns and if you make some loops, you'll have more of the wire in the field. And so let's see what they say about that, right? So the diagram, uniform field, it needs to be uniform, meaning field lines equally distant. Look at here, they've only drawn 2 field lines, but that's perfectly fine. Here they've got, I don't know about this one. This doesn't look symmetrical to me. I like this one because they've got it kind of looping around. This seems to be cut off. I don't know about that one, okay? But minimum one correctly drawn loop outside the solenoid or divergent field outside. Okay, so you could just have it kind of coming out. I said 1 down the middle and then 2 on either side, but either way. Okay, in part double I, when they change the direction of the current, we're going to flip. We're going to change the direction of the magnetic field, something like that we had said, okay? Reverse polarity is a nice way of putting that. And any one, we had said more turns or a stronger magnetic field. You could add in an iron core, I guess, if they didn't have one. Greater number of turns. Okay, you want to increase with a stronger magnetic field. It's not about them being larger. It says ignore. It's not about larger magnets. It's about stronger magnets. It's about their field lines being close together. About you have having a larger flux density. Okay. All right, and powering on through here, now we've got a 6-mark written answer here about how we might use this potential divider and the LDR to turn on a security light when it becomes dark. This is how your little night lights at home work and that sort of thing as well. Okay, so potential divider, we know that the 5 volts is split across these 2 resistors. We know that with LDRs, when it's a very, very bright and there's a light input on it, then we know that the resistance is very low. If that resistance is very low, think about V equals I times R. Low resistance means low voltage across it. More voltage across this control resistor here. Okay? And then what happens when it gets dark out and there's less lighting here? Well, then the resistance of the LDR is going to increase. When it increases, there'll be a larger proportion of voltage across it, less across here. Larger voltage across here, that's going to be some other circuit, some light connected to that, and that's why the light goes on. Let's take a look at how they would answer this one. Okay, we're shooting for level 3, I would hope. Describes less light increases the resistance and explains how the potential divider. So make sure you discuss this. Okay, quality of written communication does not impede communication of the science. So obviously you want to kind of know what you're talking about. You really need to practice using your vocabulary, your terminology, and expressing things concisely. Okay. In low light, LDR is greater, and that gives a higher share than in low light. Yeah, that's what we've said. Yeah? Okay. So explain how the potential divider. Don't just talk about LDRs. Some of you I know would do that. Make sure you're talking about the potential divider as well. And again, it should be an easy 6 marks. And that takes us to the end. I realize that some of these questions can be kind of difficult if you don't have maybe a kit in front of you for your motor. I know your left-hand, right-hand rules, these types of things you're going to need to practice. Catch some videos online. There's some good stuff on Khan Academy. There's some other GCSE-oriented videos which have diagrams and illustrations. And like, for example, there's a lot of simulations on the FET Colorado site. I would recommend you take a look at those. Okay, if you don't have anything hands-on, at least look at some videos and some 3D diagrams, that sort of thing. If you're interested in a little more detail, but also kind of the basics, I know the U.S. Army had a really good video as well. It's a little dated, but it gives you the basics of what you need. And it's actually done in a surprisingly good way considering how cheesy it was in the 60s. Thanks a lot for watching. Good luck with your practicing. Make sure that you are trying to use the vocabulary terms that you know and articulate these answers so you can get what they're looking for in the mark schemes. Practice, practice, practice. See you next time.